Hello, my name is Avi Kantha, and today I'll be presenting my Lab 3 circuits in Physics 2012. So for my introduction, this lab aims to predict and explore circuit behavior through parallel and circuit resistors to measure current and potential with different multimeters and to look at a lot of resistor and capacitor behaviors. We'll be using a circuits kits in which we connect wires, capacitors, batteries, and multimeters in order to make observations. Some final observations that delta V equals 0 and resistance increase means that increase in charging to starting time. System circuit surrounding everything else. Some important laws are Kirchhoff's voltage law, which is V loop is equal to 0, and Kirchhoff's current law, which is the I in is equal to the delta I out. And then we have all the resistor and capacitor laws in relation to V with the equation and the series and parallels. So this is a little preview of our results. In part 1 we have a series circuit. We are given two 1.5 volt batteries, two resistors of 45 and 100 ohms, and two ammeters. And in our findings, we found that I1 is equal to I2 is equal to 18.5 MA. And on negation reversal, we negate it, meaning it's negative 18.5. And the voltometer is supposed to be 3 volts, but the potential reading gave us 0.9 for 49 ohms and 1.9 for 100 ohms, which made the potential difference 2.8 volts. The potential value was 2.8 when it should have been 3. Some potential errors include inaccurate measurements, battery not being fully charged, and or having resistance in the wires, and the surrounding acting as a conductor, hence skewing the results slightly. So this is a graph that we created. In order to interpret the graph, we know that the ammeter reading doesn't change due to having a very low resistance, meaning good flow of current, but the voltometers have resistance, and hence it'll alter the current. In our part 2, we have an RC circuit. So the initial conditions given to us is two 1.5 volt batteries, one 1F capacitor, one 10 ohm light bulb, and one 20 ohm light bulb. And what we do at first is we observe the behavior of the capacitor charging. And so we connect a battery to the bulbs and capacitor in series to observe them, describe the brightness of the bulb. And the bright bulbness decreases over time as the capacitor charges. And when disconnecting it, uh, what happens to the bulb brightness is also decreases as the capacitor discharge. And the capacitor charging time is 15 seconds, while the capacitor discharging time is 15 seconds also, which is the same time. And some possible errors could have been the surrounding could act as conductor, battery may not be fully charged, and or have resistance, and readings may not be accurate. So what if we charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor and to reach full charge? Would this prediction happen in real life? Well, when you charge a capacitor with no resistor, the current will flow a lot better with zero disruptions. Hence, it would take a lot quicker to charge. Would this prediction happen in real life? Well, it wouldn't, because each wire and everything in real life has a built-in resistance that we cannot get rid of and have that perfect ideal scenario. Therefore, you won't be able to get that quickness with the current that we would like. Thank you.